Here is problem number 2 now. Analyze the given beam using stiffness method. F support A rotates by 0.002 radians clockwise. Here it is shown support A rotates by 0.002 radians. A precondition is given. Support B settles down by 0.75 inch. So 0.75 inch it settles down at B. And support C settles down by 0.5 inch. So support C settles down by 0.5 inch. Actual settlements now, rotations are involved. So we will use the actual values of E and I. E is given 30,000 KSI, means it's a steel structure. This moment of inertia is given 800 inches to the power 4. EI now feet units we will be using and the kip units. So let's convert this EI value now into kip feet unit. So it will become 30,000 multiplied by 800 divided by 12 to the power square. Why? Because KSI kip per inch square and this is inch to the power 4. So inches square is going to cancel with inches square. Still we will be left with inches square in the numerator, and to convert that inches square into the feet unit we need to divide this by 12 to the power 2. So 30,000 multiplied by 800 divided by 144 will give you 1,666.67, which is written here. So whenever we have EI values, I'll be putting there 1 with 566.67. Now you can see the geometry of this beam. At A we have fixed support, at B we have roller support, at C we have roller support, and this D, let's we take this as point D, it's a free end. So we have an overhang portion also, which is 6 feet now. If we look at the total kinematic indeterminacy of the structure, so 2 is coming from joint B, 2 degrees are coming from joint C, and 3 degrees are coming from this free joint. So it is a total now 2 plus 2 plus 3. It's a 7 degrees indeterminate problem. It will be very hard now to solve this with manual calculations. If we ignore the axial effects, so then it is becoming 2 from here, 1 from here, and 1 from here. So it is becoming 4 degrees indeterminate problem. Now somehow if we can handle this overhang position now to minimize our calculations, then we can reduce it to 2 degrees indeterminate problem, which will be rotation at B and rotation at C. Now with manual calculations, very easily we can incorporate the effect of this overhang 6 feet portion. How we will do it, I'll be telling you that how much moment it will be causing and how much shear it will be causing at this joint C. So at joint C, if we take its equivalent effect, we can now disregard this overhang portion. We can take its actions directly here. So this will become our 2-span problem then, having roller support and roller support, and this overhang portion we will disregard because we will be taking its effect on the equivalent effect on the C joint. So now it's a very comprehensive problem now, having the rotation now scenario, having the deflections also, the settlements also, and having the overhang portion also. I'll hold for a second now. Hello. वालेकुम सलाम फयाज संग खैर दे बिल्कुल ठीक ठाक खैर दे अल्लाह फजल दे बिल्कुल ठीक ठाक खदा ते शु जावाले सोर दे जा बस टिक शु लेक्चर के ऑनलाइन में बया इंशाल्लाह तफसर रहता को जा से जुड़े बराबर खुशहाल अस्सलाम ओके सो Now in next slide, let's see what we are doing to this problem now. So step number 1, we selection of redundant joint displacements and assign coordinates at those locations. Also compute AD values. So now if you see here, the overhang portion I have separated this. Why? Because I'll be taking its effect, which is 36 kip feet. How this 36 feet is coming? It is 2 times 6 divided by 2. So this is the moment because of this overhang portion at joint C. 2 multiplied by 6 is, it gives you equivalent this resultant pointed load, and its moment arm is 6 divided by 2. So 2 times 6 divided by 2, it is coming 36. And its equivalent moment now we will put here at joint C now. How much will be the shear because of this overhang 2 kip per foot load? It will be 2 times 6, which is 12 kip. So 12 kip, we will add this effect also. So the effect of overhang part is taken as, now you see here, if this 36 we put it here on joint C, so MCB will become equal to 36 and it will become in the clockwise direction. Now our unknown joint displacements are D1 and D2 now. So from 7 degrees, you see how we reduce it to the 4 degrees, and smartly for manual calculation, we can reduce it to 2 degrees now. We will be solving a 2 degrees kinematically indeterminate problem. So rotation at B, which we call D1, and rotation at C, which we call D2, we now are going to designate them as our unknown joint displacement. So here you can see D1 and D2 is equal to unknown. Now corresponding to them, we look at the actions now and the actual structure. So corresponding to D1, if we come to joint B, we don't have any externally applied moment now, so we call it 0. And this 36, it was in the clockwise direction at joint C. So now external effect, which is 36 kip in the clockwise direction, which is corresponding to D2, we include this in the AD matrix at D2 location. So this is how we get this 0 and 36. The effect of external moment is included. Quickly, we will be moving now. This was something needed explanation. Rest the procedure I'll be explaining. This is now the basic determinant structure. At B, we have a fixed support. At C, also we have put a fixed support. So those locations are clamped for the rotation now. So this is our restraint structure. Next, now generation of now the ADL matrix. ADL matrix now, it is going to be having 4 components now. First component will be coming from the actual loads, then will be coming from the rotation at joint A, then from the settlement at joint B, and then from the settlement at joint C. Now these were in the actual structure. So we will have to now add all these effects up at the corresponding 1 and 2 locations, and we generate the ADL matrix. Coming to now the effect of due to direct loading. If you see now this 30 kip, it was not at the center. It was 10 feet from support A, and on the right hand side it was 15 feet, so it was off center. In the BC span, we were having UDL. You can go and verify these values here. This was the actual structure. So this 10 feet you can see for the 30 feet means the remaining is 15 feet. And here it was UDL. So 2 kip per foot also you can see. The direct effects we are calculating now. So the equation formula is PAB square divided by L square. P is 30. A is 10 feet in this case, B square will become 15 square divided by L square will become 25 square. So 30 multiplied by 10 multiplied by 15 square divided by 25 square, it should be giving you 168.4 kip feet. For the right hand side moment for this AB span, it will become equal to BBA square divided by L square. So 72 times 15 times L, this 10 square divided by 25 square. This way we are going to get this 72K. These vertical reactions you need to find out. You have the unbalanced moment now. If it was this way, so 30, if the unbalanced moment was not there, you can split them between A and B. It will, on A, it will become 30 times 15 divided by 25. On B, it will become 30 times 10 divided by 25. So this is because of if it was a simply supported case, but now we have fixed and we have the unbalanced moment. The unbalanced moment you need to find out. So how much it is coming? It is coming 168.4 minus 72. And it will be in the counterclockwise direction. Whatever value you need to divide this by the span, which is 25, and you need to apply that in the balancing couple, which will be in the clockwise direction. So whatever balancing couple you get, you will have to add them up with the reactions which you found with this simply supported condition, and the resultant are going to be these one, 19.44 and 10.56. These are the support reactions now. On the right hand side, WL square divided by 12. These are the member end moments now. So W is 2. L square 25 square divided by 12. So it should be giving you 104.17. Right hand side, again it is the same way. Now coming to the ADL1 prime, why we are putting prime? Because we have more components also coming because of this component, these settlements and rotations. So we will put them accordingly, double prime, triple prime, and let's say tetra primes. ADL1 will be corresponding to D1, which was the rotation at joint B in the clockwise direction. So we have plus 72 minus 104.17, which is giving us minus 32.17. This is ADL1 value, ADL1 prime value actually. So it is the algebraic sum of these two moments now at coordinate 1, which is joint B. Similarly, ADL2, it is corresponding to D2, so which is plus 104.17, so 104.17 we have. Now, turn by turn, let's now include those rotations and settlements also. Now, second part of this ADL will be coming due to indirect loading. That is now indirect loading we are taking now. So the direct loading already we did, the gravity loading. Now the indirect loading because of the rotations and the settlements. So 0.002 rotation at A, clockwise rotation at A we are including, and these values whatever we get we will call them ADL double prime. So here you see now rotation, this 0.002 radians is applied at A. This yellow line is rotated to this inclined red line, and this is 0.002. We already said that it will be equal to 4 EI theta divided by 25. So 4 times EI was 156.67 and theta is 0.002 now. So we put the actual value of 0.002 here divided by 25. You should be getting the value of 53.33. To the far end, it will be half amount. So half of 53 is 26.67. Now this we need to balance now. Here we have fixed this. We have claimed this C joint. It is not going to shift this moment to the right hand side. So now to balance this clockwise movement, which is the summation of 53.33 plus 26.67 divided by this span, which is 25. So it is coming 3.2, 3.2, and you can see its sign also. The unbalanced movement was in the clockwise direction, so this should be in the counterclockwise direction. So quickly, if you do it, 53.33 plus 26.66 divided by 25, you should be getting this 3.2 and 3.2. Now ADL1 double prime and ADL2 double prime. So corresponding to D1, now we have 26.66 clockwise. From BC span, we don't have anything. So 26.66 here you see. corresponding to D2, which is at joint C rotation. Here we don't find any action, so it is 0. So we have taken this value. Now we go to the how we include the settlement. The settlement, if you see, the settlement here was 0.75 inches. As we are using now the feet unit, so divided by 12 will give you 0.0625 now. So due to indirect loading, that is due to settlement at B now, here we provide a guided roller now, and we assume it is settling down. The other two locations we are going to put now blocked now. As we already discussed, because of this settlement, how much action and how it will be generated. Look, from the left hand side span, it is trying to come back. So this is counterclockwise movement. From the right hand side, again, it is trying to come back. So it is causing clockwise movement now. How we find out its magnitude? Its magnitude will be 6 EI delta. Already we have 0.0625 divided by L square now. So CR, you should be running this number now. 6 multiplied by 1, 5, 6 is 0.67 multiplied by delta, which is 0.0625, and divided by L square, which is 25 square.
There is 0.94.
0.94, sir.
0.9? No, why it should be like this? Look, 6 multiplied by 156 is 0.67.
Sir.
It's 100.
It's 100, sir. Yes, sir.
Okay, so 100, and we are showing 100 also, right?
Yes, sir.
0.0625, okay, and divided by L square, so 25 square. This is why always I urge you that you should be sitting with the calculator so that you make practice also. Sometimes you know how we should apply the equation and what numbers we will be multiplying. But when you actually do it on the calculator, you make mistake. Now you saw the example also. So this 25, this 100 and 100, now you see luckily the 25 was on the right hand side, so that moment is also calculated. At the far end, their signs are going to shift in the same direction. In the same direction you see for the left span and for the right span. The balancing couple is now simple. Here for the left span, BA span, if you take 100 plus 100, so 200 is the unbalanced moment. Now we need to balance it by a couple. So multiplied by 24, this divided by 25, span is 25. So 200 divided by 25 is 8. You see here now, the unbalanced moment was in the counterclockwise direction. The balancing should be in the clockwise direction, and its magnitude already we found it is 8 K. So this is giving now contribution due to settlement at joint B. Now you see here how we are sliding it down and how towards the support it is 0 now. It is not going to affect directly the settlement at support A and C now. So this 100 kip at B now corresponding to now D1 we are calculating the actions. So counterclockwise and clockwise both are 100, 100. They are balancing each other. So the effect is going to be plus 100 minus 100 is equal to 0. 0 we are writing here. ADL2 corresponding to D2 clockwise is our positive direction 100. So we are writing 100 now. With this now you should be able to now project now or present your settlement at C now. When we are applying the settlement at C, which was 0.5 inch, you should be having clamp condition at B as well as clamp condition at A also. So quickly you should draw it so that we can match it then. You show a settlement at C, you provide a roller guide there and slide C point down by 0.5 inch. 0.5 inch divided by 12, whatever feet is coming, so that will come. So this is now the situation. Look, A and B are claimed at the original position, but here at C we are sliding it down by 0.5 inch. Now settlement, it will try to go back 6EI delta 8 delta. This C actually, this is not A, this is C now. This is MC, so these are slight collections. So Faisal is there, so he should be realizing these mistakes now. So because of the C. So this is C now. And let me go now to the slideshow. So here now you see 0.5, so it is equal to 0.04. Again, you can now verify these values. 6 times 1.56 is this was 156 is 0.67. Delta C is now 0.041 divided by L square, so 25 square, so 66. Far end it is going to be the same. And you can find out the balancing couple. It was counterclockwise unbalanced, so balancing couple is. So due to this settlement, now we found these all member inductions. ADL1 with 4 primes, now it will be corresponding to D1 now, which is minus 66.67. Why minus? Because it is counterclockwise, so we take the effect. If from the BC span something is coming, so we should be able to include that one also. ADL2 triple prime, again, if you see now, so corresponding to this, again, counterclockwise movement we have corresponding to D2, so minus 66.67. Now you have ADL 1 prime, double prime, triple prime, and then 4 primes. So you should be adding these effects in order to get the total effect of ADL. So here now you see ADL 1, all these primes, which were the values now, already you have them, ADL 2. So already those values you have. So this is now the net ADL matrix, minus 72.17, and ADL2 is a 137.50. ADL1 is minus 72.17, and ADL2 is 137.50. Now remember, when you go to AML matrix, so you will be taking the effect of all these 4 from where you generated these ADL matrices. So correspondingly, you will be adding in the AML matrix. Similarly, in ASD values, ASD or AMD values, those will be generated from where we will generate now the stiffness matrix. And stiffness matrix, it is now the routine method now. What we do now, again, corresponding to D1 clockwise, we are providing this. You have all these values, you should be able to now do it. This is coming from 4EI theta divided by L. Here by half amount, and this is the balancing couple now. Here again, from the right hand side, you can see the same situation. Now your AS11 will be this 246.67 from the left side, and from the right side, these are the corresponding values to your D1. So you add them up, both are in clockwise direction. So this summation is giving you 543, these 43.33, and S21 is here, this value, so we write it here. Clockwise, so these are coming positive. Now corresponding to D2, now we are going to apply the unit. Rest of the positions will be clamped or locked. So here again you can find out it is half of this near end. This is the balancing couple. So whatever movement actions you have here corresponding to D1, that is our S12, and whatever you have corresponding to D2 now, that is your S22. This way we complete our this stiffness matrix. We go to the next slide now. We are in a position to generate or find out D1 and D2 values. So equilibrium equation, we put these values. EI already it is accommodated in these values. So D1 is coming 0.0026 now, and D2 is coming 0.0051 now. Next now, member inductions. Lest we are finding out these member inductions. Accordingly, now you can go to the diagrams from where you generated the ADL matrix, or from where you generate for the AMD values, you can go to the stiffness from where you generated the stiffness values. So here now, look, AM1 now let's verify AM1 is here, right? At A, this shear we are taking in the upward direction, AM1 now. Now let's see how this 24.44, I'm going to verify this one AML values, rest you need to verify now. So let's verify how this 24.24, you make a note this CR that AML1 calculated is 24.24. You make a note and let's see how it is coming now. So let's go to the ADL matrix now. ADL matrix was generated here. This was from the direct loading. So we have plus 19.44. This is due to the direct loading. Did you write now 19.44? CR?
Yes, sir.
Okay, next now, this is because of the rotation. So because of the rotation, we have minus 3.2. So plus 19.44 minus 3.2. Next, because of this, we have plus 8. So you add plus 8 to it. And then finally, from here, we have 0 now. So you give me now the summation of all these 4 numbers. How much it is coming?
24.24.
24.24. So this value is confirmed now how we calculate. Accordingly, you can calculate now AML2, 3, 4 up to AML7. So you go and practice it. All the numbers are given, so you need to verify them. Similarly, now we go to the AMD corresponding values now. The first one, AMD 11, 21, 31, and so on, they are going to be generated from where we generated the first column of the stiffness matrix now. So here, if you see AMD 11 will be equal to minus 1600. So this one is plus 16, minus 16, and plus, and so on. And similarly, the second column will be generated when we go corresponding to D2. So this from here it is. From here, the AMD 12 will be 0. AMD 22 is also 0. AMD 32 is minus 1600. So here now you find out that minus 16 plus 0, 0 in this one. Very easy. You can do it very quickly. Now, when these are now in hand, you can go plug in this equation. AM is equal to AML plus AMD times D. And directly now you go here on the right hand side. If you see the final column, these are now all those shear and unknown moment values. Once you get them, accordingly you put them on the sketch now. Here you see all the support reactions. And with the help of this now, if you see here now, the support reaction at C, it is 23.68. This you need to verify now, whether it includes the right hand side or not. If not, then you will have to put that separately. So this value you need to verify. So after this, you need to draw the shear force and bending moment diagram, which is a routine subject now, so you should be able to do it. Any question? Okay, with this now we go to problem number 3 now. And problem number 3 is analyze the given beam using the stiffness method. We are looking at A, B support, but from support A, if you see in the middle, we see this yellow now circle now, solid circle, which is a hinge now, construction hinge we got. Now, how we solve such kind of problems now? We have a construction hinge. At construction hinge, we said it is going to be indeterminate by 4 degrees. 2 translations, vertical and horizontal, and 2 rotations now. And here now you can see, if we ignore the axial effects now, so it is becoming 3 degrees. Horizontal translation we are going to ignore now. So here now, if you see theta here at this point, so the left hand side theta, it is going to be more than the right hand side, the side theta. This theta 1 and theta 2, this one, if you take at joint B and joint A, they are not going to be the same. Why? this theta 1 will be vertical divided by horizontal, which is 10 feet. And this theta 2 is going to be vertical, which is delta divided by the same delta divided by 20 now. So it is going to be half of whatever we have at A now. So that is why we have two independent rotations here. We need to find out both rotations here. So at this hinge now we have two rotations unknown, and then one translation, which is the vertical deflection. So we solve this as a 3 degrees indeterminate problem. How? To the left, this rotation we take D1. To the right, we take this rotation D2. And vertical settlement, we take this D3. These are the 3 degrees of indeterminacy. Two rotations and one translation at internal hinge are taken as redundant joint displacement. So D1, D2, and D3 we take unknown. Corresponding to this, if you look at in the actual structure, we don't see any moment to the left, any moment to the right, any now vertical reaction even, vertical action even at this joint. So means if vertical action was there which was corresponding to D3, then you need to include that as AD3 now. But now here we have all zero, so we complete this AD1, AD2, and AD3 0, 0, and 0. Let's move now to the ADL matrix. Very easy. This is first now we are showing the restraint structure. The internal hinge, we are just converting this into rigid or this fixed support. Fixed support is always a basic kinematic determinant structure or joint. Here now we expose this under the actual load. So at that D1, D2, D3 location, which was the hinge, we split this. So we put there a restraint or a fixed support. So we split this structure into 2-1. Here 10 feet you can see. Here you can see this was, I think, 15 feet, not 20 feet. CR, what was the value here?
20 feet, sir.
It was 20?
Yes, sir.
Oh, yeah, okay, 20. So 20 is fine then. Okay, in the previous one, actually, the pointed load, it was 25, so 10. And so I was having that thing in my mind. So 20 is fine then. Fixed end actions, again, WL square divided by 12 now. So W is 1.5 times 10 square divided by this 10 WL square divided by 12. So W is 1.5, 10 square divided by 12. 12.5 we are putting. We don't have any unbalanced moment because 12.5 clockwise and 12.5 counterclockwise, they are balancing each other. So no unbalanced moment. So simply 1.5 times 10, which is 15. So 15 out of this 15, half is going to the A support, half is going to the this internal hinge location. So 7.5, 7.5. Similarly, these calculations you can run for the this right hand side. So here W is 1.5 times L square, 20 square divided by 12. So 50 and 50 are coming. Now corresponding to D1, if you see, we have 12.5 in the clockwise direction. So this 12.5 we have recorded as ADL1. To the right, we have 50, but this is in the counterclockwise direction, which is opposite to the D2, which was clockwise. So we put minus this 50 now. And corresponding to D3, which was downward direction. So to that corresponding, we have 7.5 and this 15, but both are in upward direction, opposite to that D3 direction. So minus 7.5 and minus 15, so minus 22.5. These are now the ADL3. This is how a very good example how we get the corresponding values to these, the corresponding values of these, how we pick them from the sketch. Next now, ADL matrix is generated that easily. Next, now we go, why we are, look here, we are taking independent now these movements, because we took independent rotations, D1 and D2. So that's why corresponding values we are taking in, including them in the ADL matrix. Next, now we go now to the generation of the stiffness coefficient matrix. It will be complete. So first, a unit rotation is applied at location 1, and we prevent rotations at 2 and 3. That is, D1 is equal to 1 we are providing, and D2 and D3 we are putting equal to 0. And this way we generate the first column of the stiffness matrix, which will be S11, S21, and S31. Here now you see, corresponding to D1, which was the rotation to the left of this hinge now, clockwise rotation we are providing. The right rotation we are now clamping, and the translation also we are clamping. We are not allowing any translation in this direction. When we provide a clockwise rotation now, so 4 EI divided by L, L is 10, so it is simply 4 divided by 10, which is 0.4 EI. At the far end, it will be in the same direction, so clockwise, and 0.4 divided by 2 is 0.2. Balancing couple will be 0.4 plus 0.2, 0.6 divided by 20, so 0.06. That easily these member inductions are generated. On the right hand side, we have a fixed support. We don't have any rotation or settlement condition. No actions will be generated. So everything is equal to 0. S11 will be whatever is corresponding to now D1 now. So 0.4 was there. So you see here S11 is 0.4. S21 will be whatever is corresponding to D2 now. So that is 0. So here we put equal to 0. Settlement now, corresponding to settlement, we have settlement D3. If you remember, it was in the downward direction. Originally, we assume it positive. But here we have 0.06 from the left support. From the right now, we have 0. So it is simply minus 0.06 EI. So minus 0.06, it is becoming our S31 now. Is it clear now? CR.
Yes, sir.
Okay. So then now corresponding to D2, we are going to apply a unit rotation now, and D1 and D3 we will be putting equal to 0. Here you can see D2 is equal to 1, D1 and D3 is equal to 0 we are putting. Now corresponding to D2, we are allowing rotation now, unit rotation. Here it is clamped and the settlement is also clamped now. When we apply a unit rotation corresponding to D2 now, member inductions will be generated. From where this 0.2 is coming, this 0.2 is coming from 4 EI divided by 20. Far end, it is half of this, so 0.1, and this is the balancing couple now generated. Once we have these numbers now S12, this is now S at 1 due to 2, which is 0. So here 0 is written. Here we don't have any action corresponding to D1. Corresponding to D2, clockwise action we have, which is 0.2. So 0.2 is included here with positive sign. And at D3, which will be the vertical reactions at this corresponding to this 3 now, which is minus 0.0, not minus. This is now in the direction of D3, so it should be positive. And you see here, it is 0.013 EI. If something is coming from the left-hand side also, you take the algebraic sum then, 0.0. So this is how the second value of this stiffness coefficient matrix is generated. And third now, D3, corresponding to D3, we are going to provide 1 now, unit translation, and D1 and D2 we will be putting equal to 0. And how we can provide this? We can provide this if we provide a roller guide there. So this, if you see here, this support is sliding down now in the direction of D3, which is equal to 1. This will try to come back now to its position. This is how we find out the direction of this one. This will try, the right hand side will try to come back now. So this is how the direction of this is. How the magnitude, it will be 6 EI delta R divided by L square. So L for this side is 10. You put them in value in this equation, get this value. Far end, it will be the same amount, the same sign. balancing couple, it was counterclockwise. This is clockwise. Similarly, for the right-hand side portion, this will be 6EI delta divided by L square. So L is 20 now. This is how we get 0.015. Far end by the same amount. And this is the balancing couple. Now, unbalanced moment from the right-hand side, the span was clockwise. So balancing couple is in the counterclockwise direction. Look for the corresponding values now, corresponding to D's, our D's now. Corresponding to now D1, we have minus 0.06, and here it is written, and it is our S13 now. S at 1 due to 3. 3 in 3 direction we are applying this unit displacement. S23 will be 0.015y plus because it is in the clockwise direction, same as that of D2. And D3 will be the summation of both are positive in the D3 direction. So 0.012 plus 0.0015. So it will give you. So this is actually your S33, not S32. This is your S33. So again, I'll have to make no correction here. We have some mistakes. S33. So we found 1, 3, 2, 3, and 3, 3 also. So with this now, I go to the presentation. And now here now you see this is again is 3, 3. So need to make these. S33 here you see this value, it is here now. So we make a matrix form. Now after making this matrix form, we put this in equilibrium equation, all the numbers we have. So you can run these matrix algebra now and you can find out D1, D2, and D3. After this now finding, it's now the routine one. Now let's we find out AM1, AM2, AM3, 4, 5, and 6. By the way, how much should be AM1 and AM5? It's an internal hint, so AM4 and AM5 by observation you can say these should be equal to 0. And from calculations it will be coming equal to 0. So AM1 now these corresponding values AML and AMDs you should be taking from their corresponding locations. Now here now if you see AML corresponding AM1 was here and AM2 was here. So if you see here, it is 7.5, so we write it 7.5. AML2, this is this 15 reaction, so 15 reaction here. AML3, if you see, AML3 corresponding to this one, this actually is opposite to the assumed one, minus, so this should be minus 12.5, you can see. AML4, this is plus 12.5. This AML5, this is clockwise, this is counterclockwise, so this should be minus 50. And AML6 it should be plus 50 because sign are matching, so 50. Similarly, now we go and the AMD matrix we generate. First, already you have this data now. So this D11 should be your minus 0.06 EI. AMD here 21 we have 0, so it should be 0, and similarly rest of the values you can pick and you can complete the first column of the AMD matrix. Similarly for the second column where we applied the D2 is equal to 1 theta here you can see, and all these corresponding values you can pick for the AMD matrix. This will complete the second column of the AMD matrix. For the third now where we give the vertical settlement, unit settlement, so from here you will pick the corresponding values and you will complete the third column of the this AMD matrix, and here you can see all these numbers now. Now we have AML, we have AMDs also, we have Ds also, so you put them in this equation and find out these values. So reaction at A, it is coming 24.38. Reaction at B, it is 20.67. This moment at A, which was our AM3, it is coming minus 160. So Initially we took clockwise, but with negative sign we are reversing the direction. Here you see now AM4 and AM5 0 0 are coming, so we put them 0, and they must be 0 because it's an internal hinge now. And then AM6 now it is coming plus, so means clockwise, so 112.5. After this, we draw the shear force and bending moment. Here you see at hinge we have 0, it should be 0 here. Rest you can complete it. After this now, these are now your assignment problems. So you should be looking at your assignment problems and you can coordinate with the TA now which one problems you should be solving and how you will be submitting them. So he will give you now. So next now, these are the references. So these three problems were very much comprehensive. Now, if you look at the very first problem was a simple one, only carrying the pointed load. The second problem, we involved the rotations and the settlements also. Even we involved the overhang portion also we solved it. And in third problem, if you see, we involved the internal hinge also. If this internal hinge we put in the middle, let's say, and if we have fixed support, then you will have to solve this smartly. Remember, if you take the more degree of indeterminacy, somewhere now you should be utilizing your judgment now, engineering judgment, that how can you reduce your work. Otherwise, if you can include the fixed support now, degree of indeterminacy also, but what will happen after going through all those laborious calculations, finally you will be getting there the giant rotations and the giant settlements are these translations and rotations equal to 0. So what is the purpose of doing all these things? Because by observation you can see that is why we don't include them in the indeterminacy. That is already understood that those displacements at the fixed joints are equal to 0. Now the time is, let me check my clock now, it is 1:40 now almost. So if you have any question, you are welcome to ask, otherwise we are done for today now. And is there any announcement about the midterm examinations now, CR?
No sir, अभी तक तो कोई announcement नहीं हुई सर.
नहीं है अभी.
नहीं sir.
And is there any policy also? Let me stop this recording. So I have stopped the recording.